In this video, we're taking a look at electrochemical cells, voltaic cells, dry cells, lead storage batteries, and fuel cells. So in chemical reactions, we have energy being absorbed and released, and oftentimes that energy is in the form of heat, but some actually involve electricity, flowing of electrons. And so we can use that flow of electrons to create energy in terms of electricity, like in batteries, when we make electricity through an electrochemical process. We also can use the electrochemical process to purify elements. Sodium and aluminum are only found in compounds, so in order to get them purified, we run electricity through them to then run that reaction in reverse to isolate those elements. And your nervous system also uses electrochemical processes to send signals. That way, when you get pinched, you feel that pain as it goes from your arm up to your brain, telling your brain, ouch, that hurts. So these occur in a spontaneous redox reaction. We'll take a look at zinc with copper sulfate, where zinc is more reactive than the copper. It's going to replace the copper into the sulfate, and the copper is going to plate itself onto the zinc. The ionic equation is zinc plus the copper ions in the copper sulfate are then making zinc ions and copper. So electrons are being transferred from zinc to copper as zinc is oxidized and copper is reduced. And so this spontaneous reaction, since zinc is again more reactive than copper, is going to then cause the oxidation reduction reaction to happen between the zinc and the copper ion. So zinc again being oxidized, copper being reduced. And here we see that zinc being placed in the copper sulfate on the left, and then the right where the copper coming out of solution, it's becoming less blue, it's much more faded, almost clear at this point, and we see all the copper that's being built up on that zinc as the zinc is reacting with that copper again, reducing the copper to its elemental state as the zinc is becoming oxidized. So in these redox reactions, anytime we're taking chemical energy and changing it into electrical energy, we call that an electrochemical process. It always involves redox reactions because there's always going to be this transfer of electrons between these two different substances. So unlike what we just saw though with the zinc and the copper, when you have these two redox reactions happening together, you can't capture those electrons as they move. So we got to take those two separate processes, the oxidation and the reduction half, and separate them from each other. That way we can have these electrons flowing through this external circuit from one to another, where we can again get that electrical potential. And so any device that will then produce electrical energy through these two different half reactions, the oxidation and reduction half, is called an electrochemical cell. So the first person really to notice this electrical energy coming from chemical energy was Alessandro Volta back in 1800. So now any reaction that involves taking chemical energy, converting it into electrical energy, is called a voltaic cell after Alessandro Volta. And it's again done through these spontaneous redox reactions, in the forward direction as they prefer to occur, taking one substance being oxidized and another substance being reduced. So how do you build a voltaic cell? Voltaic cells again involve two different half cells, a reduction and an oxidation. And then in those oxidations and reductions, you're going to have a metal electrode, so two separate metals, in a solution of their ions, and then a salt bridge that's going to connect them. That way we have these ions being able to flow to one side and another to keep those solutions neutral. Because as oxidation occurs and electrons that are being lost, you're going to have a buildup of positive charges, and as reduction occurs and you have these electrons flowing over to that side, you're going to have a loss of charge, you have a negative charge. So the electrode that's where the oxidation is occurring, which is creating electrons, is the negative side. We call that the anode, because again, as it oxidizes, it's going to lose electrons. And then the other side, where the reduction's happening, we call it the cathode. We call it the positive side because it's absorbing those electrons. And again, as the oxidation occurs, the electrons move from the anode to the cathode, where the reduction will occur in the other half, and the charges again will remain balanced. So again, on the microscopic level, over on the anode, where the oxidation is happening, we have electrons that are being produced, and then they flow over to the cathode, where the cathode then will take those electrons and they will reduce down a metal, and those ions will then be moved through the salt bridge to keep the positive and the negative charges balanced on either side of our voltaic cell. So when setting one of these up, again, we're going to have the anode, where the more reactive metal, which is going to be oxidized, we'll put that on the left. They come both first alphabetically, anode before cathode, oxidation before reduction, plus the two vowels match up. So we have zinc electrode sitting in the zinc sulfate, again connected by an external wire for the electrons to be able to flow over to the cathode, where now those electrons are going to reduce down the copper. So again, cathode reduction, the two consonants together. Again, they come second alphabetically. Again, that's the positive side because we have the electrons flowing, being absorbed on that side. The negative side, where electrons are being produced. And again, we see the salt bridge. This time it's potassium chloride, where now the chlorides are flowing to the oxidation half to balance out those zinc ions that are being formed. And then we have potassium ions, which are flowing to the reduction side because as copper is being reduced back to its elemental state, you're going to have a buildup of those negative sulfate charges. So we have potassium ions to balance those out. So rather than have to draw this picture out every time, we can represent these electrochemical cells with shorthand line notation. Shorthand line notation gives us an idea of what's going on with our anode and our cathode, which things are in contact with each other, which things are connected through a salt bridge. So for our zinc copper voltaic cells we just saw, we have zinc and then single line zinc sulfate, double line copper sulfate, single line copper. The single line showing things that are in direct contact with each other, the double line showing those that are connected through the salt bridge. Again, just as we saw in our picture, it appears left to right. So again, the anode's going to go first because anode comes first alphabetically, and then left to right across all the way to our other electrode. So we can use these electrochemical cells to get energy. And one very common place to see this is in a dry cell, where instead of now having those solutions of those ions and the electrodes, it actually is a paste. We see this in our regular household batteries, AA, AAA, C, and D batteries. They're all dry cell batteries. They involve, again, this paste, which is made up of manganese 4 oxide, zinc chloride, ammonium chloride, and water, and then the zinc casing on the outside. So we have a graphite rod that then is in the middle that's inserted into the paste to allow electrons to flow, but they're not going to be oxidized or reduced. What's really happening is the zinc acting as that cathode, again, just carrying the electrons. The zinc casing is the anode. It's going to be oxidized into zinc oxide, where the manganese 4 oxide is going to be reduced down to manganese 2. So there's a paper that is between the paste that prevents the paste and the zinc from freely contacting each other. Again, if they're in contact with each other, we can't pass the electrons through an external circuit and actually get that electrical potential. So if that piece of paper is in there, is in any way compromised, then you're not going to get electrical energy out of your battery. It's going to just react on its own, and then it'll be all used up. So again, even though that graphite isn't there as our cathode, really again, it's the manganese that's being reduced, again, and the zinc being oxidized. The graphite is just a conductor. So here we see again, there the yellow is our manganese 4 paste, along with our ammonium chloride and that carbon graphite rod we see in there. And the zinc on the outside, again, being oxidized, and there's that porous paper in there keeping them separate from each other. Another common battery is a lead storage battery. These are the big, huge block batteries that you see inside your car. It's a group of cells that are connected together where we have lead actually being oxidized and reduced. And again, in order to get the amount of energy you need to get your car going, that big block, there's actually 6 different cells that are connected to get to that 12 volts of potential. So we see that there's a spongy lead in acting as our anode, and then there's lead 4 acting as our cathode. So lead is again both oxidized and reduced for this reaction. And the electrolyte is going to be sulfuric acid. And there's no salt bridge in between, since there's only this one electrolyte being used, and the charges will remain balanced out. So old batteries used to have to actually add water to make sure your sulfuric acid didn't dry out, but now batteries have progressed to the point where you don't have to keep adding water. They will stay moist enough on the inside. And these lead storage batteries conduct an electrical current in the forward direction, that's spontaneous direction you would expect, but in your car you also have an alternator, so once your car gets running, there's this generator that then makes electricity back and runs electrical energy backwards through your battery to recharge your battery. And here we see our lead storage battery again, 6 different cells of this oxidation reduction occurring to get to your 12 volts of energy altogether. And again, we have lead oxide, lead 4 oxide, and we have the spongy lead. So that way lead is being oxidized, lead is also being reduced with our sulfuric acid and our water. The last electrochemical process we're going to look at that gives us energy is called fuel cells. Fuel cells are nice because they have renewable electrodes. You can just keep adding in these new electrodes rather than have a battery run out once that reaction is done and be all over with. Also, you don't have to recharge them since you can just add in these new electrodes and they don't give off bad air pollutants. So most common fuel cell is hydrogen and oxygen. We take hydrogen gas through the combustion of hydrogen gas, making water. So again, no real air pollutants, and you are then getting lots of energy back. So in these fuel cells, we have 3 different compartments that are separated by 2 different electrodes, and those are made up of a porous carbon. And the oxygen then is fed through into the cathode to the hydrogen, which is happening at the anode. Again, the hydrogen being oxidized and the oxygen being reduced. There's then this 3rd compartment, which has potassium hydroxide in it to use as the electrolyte, which then keeps these charges, again, balanced out. And then these fuel cells, though, as great as they aren't really economically feasible because they're too expensive, again, for general use. We see them with spacecrafts and military vehicles, but for common everyday use, for common everyday people, it's just too expensive at this point. Let's take a look at this fuel cell. We see, again, the hydrogen on the left at our anode, the oxygen right at our cathode, with those potassium hydroxide ions in between. And again, we have electrons flowing from the anode to the cathode, where the hydrogen's being oxidized to then make electrons, where the oxygen is being reduced. And then down the bottom left, we see water. Water is the only thing that is being given off, the only byproduct of this fuel cell. Again, no real pollutants being added into the atmosphere.